So we're looking at the section applications of derivatives, and we're looking at rates of change, that is average and instantaneous rates of change. And in order to discuss the average and instantaneous rates of change, we're just going to recap some concepts such as the secant line and the slope of the secant line, the tangent line, and how we can approximate the slope of the tangent line with the secant line's equation formula and just taking its limit. Then we are going to move on to, the average velocity and instantaneous velocity. We're just going to do some examples regarding that. And then we're going to move on to the actual just standard instantaneous rates of change calculations. We're also going to introduce the fact that you don't need to take the limit. You could use the derivative in that regard near the end. And then we're going to just look at, when you have rates of change, you can work out where your function is increasing and decreasing, where it's not changing, by just understanding what it actually represents. So we're going to start off with the secant line. So as we know, a secant line is basically a straight line that intercepts your curve function at least twice. So if you have, a function like that, technically, if it goes like that, it's still a secant line. It's intercepting twice, like over there, for example, you have your 2 points that are intercepting it. So it can intercept more, but the idea is you're only going to look at 2 points that are intercepted. And a reminder, work that you used to is you have a circle, and that's your secant line for your circle kind of situation. So on our graph paper in the corner here, we have a function, which is f of x. It's the blue line there. And we are going to have, obviously, our secant line, which is the red line, which intercepts our function at points P and points Q. And we are going to look at finding the slope of the secant line utilizing the information from the function itself. So the first thing we're going to have to look at is what are the x and y coordinates of points P and Q. So point P has the x coordinate of C, and that's just, a placeholder kind of situation here just to make our lives a little bit easier. And then we're going to have Q, and Q has the x coordinate of C plus H. So the distance between the x coordinate of P and the x coordinate of Q is that H. And then we have obviously our y coordinates, and our y coordinates we can find by just putting in our x coordinates into the function. So you have, y of P is equal to the function at xp, the x coordinate at P, which in this case is, just that C situation. And we also have yq is the function with the x coordinate at Q, and that is just going to be C plus H. Okay, so we have our x and we have our y coordinates, and we know that the slope of a line is the change in y over the change in x. So we have, our change in y over our change in x, and we can just put this information in. So I'm going to do it a little bit longer than necessary, just to remind you and get you into it in a slow process. So we're going to have yq minus yp over xq minus xp, and yq sits over there. That's f c plus h minus f of c, and then we have, our x, which is c plus h minus c, and that's going to give us c plus h minus f of c, and the c's cancel out, so you have c minus c plus h gives us that h that chills over there. So we have the slope of the secant line, and a reminder that that slope of that secant line is approximating the function between the 2 points. So it's saying, an approximation of the function between the 2 points is this line that's chilling over there. Obviously, it's not super accurate, but it is a kind of representation. It gives you the broad idea of what's happening at that function. And obviously, the closer that P and Q are, the more accurate of a representation it's going to be of the function between those 2 points. And that's where your tangent line comes into play. So your tangent line is a line which intercepts your graph once. Technically, it touches the graph. It just touches the graph. It's tangent to the graph or the function. So it's going to only have that one, place where it is where it is part of the graph or the function actually. So when you think about it, how do you find the slope, or how do you approximate the slope? You would actually take that h that was, the the distance between those 2 points, and try to make it as small as possible. So let's just go to a new page. So the whole idea is, again, we're going to look at the graph paper side of our page, and we're just going to bring those 2 points closer and closer together until they're pretty much just 1 point, and that's going to give us the slope of the tangent. So the idea behind that, and let's just replay that one more time. You're just going to bring it closer and closer together, and there you have your slope of your tangent. So we're just making that h as small as possible. And that's where we still have the secant equation, where we take the limit as h tends to 0. So we're making that h as small as possible, and that's going to give us the slope for the tangent line. Okay, and as an approximation of the slope of the tangent line, it's the limit as h tends to 0 kind of a situation. So now we have our secant line and we have our tangent line. We can now move on to just a brief description of average and instantaneous velocity. So we're going to use velocity because that's something you can be slightly familiar with. You've driven in a car or bus, whatever before. So you get kind of the idea, between average and instantaneous, because instantaneous is what's on the speedometer, and average is like, say your trip is 2 hours long and you're traveling on the highway and you follow the speed limits, you would end up having an average velocity of approximately that 120 kilometers per hour kind of a situation. Whereas you will not travel 120 kilometers per hour for every second of your journey. You'll have to stop in some cases, you will overtake in some cases. Technically, you're not supposed to go over 120, but you get the idea. So that's the difference between the average and instantaneous. So we have the exact same, graph happening here, but we're just going to tweak it a bit now. So we're going to leave the secant line as it is, and we're going to show you how the velocity changes as you move from P to Q to show you the difference. So like what the average looks like versus how the slope keeps changing as you go on. So you can see the tangent line moves, and that's the instantaneous velocity kind of a situation. So you can see it tweaks and it follows your function a lot more accurately, whereas your average just gives you the approximation between those 2 points. So again, you have your average, it's like your secant line, it's your slope of your secant line. Then you have your instantaneous, it's like the slope of your tangent. So at that singular point, at that moment in time. So let's go ahead and just look at an example just to clarify and set it into your heads a bit more. So we have an object that falls in a vacuum. Falls in a vacuum to make our lives a lot easier when it comes to, working out everything. And it starts at rest P and falls at 8t squared meters in t seconds. So it is a function. It's a function of t, which is equal to 8t squared. And that function produces your m. Okay, your distance in meters. So let's not call it m. Let's call it your distance, d. So it falls 8 meters in the first second, and it sits at 32 meters at the second. So you can actually see you speeding up as you're falling, kind of a situation, or as the object is falling. We're also going to assume it doesn't reach terminal velocity, again, just to keep things simple for us. And what we're going to do, we're going to investigate its instantaneous velocity at 1 second by investigating a couple average velocities, just so you can see that, again, the average velocity will give you the average in that interval, but it's not necessarily going to be accurate, at those endpoints of those intervals or, throughout the duration of it. Just the overall, it matches. So let's first draw the diagram a little bit so we can and put some information there, and then we're going to work out the average velocity at different intervals so you can see, the differences. So we have the object and it is falling, falls this way. At 1 second, it's fallen 8 meters. Okay. At 2 seconds, it's fallen 32 meters. That was given to us, but we could work it out as well by utilizing the formula of the distance equals to 8t squared. So let's add in 1.5 seconds. So at 1.5 seconds, it's fallen a distance of 1.5 squared, which is equal to 18. meters. And let's add in at 1.1 seconds. So at 1.1 seconds, we have 1.1 squared, which is equal to 9.68 meters. So we have a couple measurements here. We're going to work out the average velocity between 2 and 1, between 1.5 and 1, and between 1.1 and 1, just so you can see the differences. And obviously, the smaller the interval, the more accurate it is for, all the points in that interval. Right, so let's start off with the 2-second one. So we're going from 2 seconds to 1 second. So we have the 2 to 1 interval. So the velocity, or the average velocity, between 2 seconds and 1 second is the distance at 2 seconds minus the distance at 1 second divided by the time, which is 2 seconds. So I'm just going to put it like 2 seconds there, and 1 second. And that's going to give us 32 minus 8 divided by 1, which gives us 24 meters per second. So the average velocity between 1 and 2 seconds is 24 meters per second. Right, so let's move on and let's do the interval, the 1.5 and 1. So we're looking at 1.5 and we're looking at 1. Average between 1.5 and 1 second. And that's the distance at 1.5 seconds minus the distance at 1 second. 1.5 minus 1. And that's going to be 18 minus 8 divided by 0.5. And that's going to be 10. And that's going to be 0.5. And that's going to give us 20 meters per second. So we have that 20 meters per second happening there. So between 1 and 1.5 seconds, the average velocity is 20 meters per second. Now you can already tell from this that, hey, between 1 and 1.5 seconds, that average velocity of 24 meters per second is not that accurate if you have to use that 24, to do any calculations or work out anything, in the future kind of situation. So you can already see, obviously, the larger your interval, the more that average velocity won't necessarily be a good idea to utilize. Let's move on. Let's move on to the smallest interval that we're going to do, the 1.1 and 1 second. So we have the velocity average between 1.1 and 1 second, and that is, your distance at 1.1 second minus your distance at 1 second divided by 1.1 minus 1. And that's going to give us 9.68 minus 8 divided by 0.1. And if we go do the math on this, it's 16.8 meters per second. Okay, so 16.8 meters per second. So between 1.1 and 1, the average velocity is 16.8 meters per second. So again, you can see how the accuracy, the smaller the interval, the more accurate you're going to have for your estimations of your velocity and even your instantaneous velocity. So the smaller the interval is, the closer you are getting to that instantaneous velocity. Now, let's actually go find that instantaneous velocity at 1 second. So we know it needs to be close to 16.8, somewhere around there kind of thing. But probably less, because remember, it's falling and it's getting faster as it falls. So it should be less than 16.8 meters per second. So same problem, we just have that second aspect of what is this instantaneous velocity at 1 second. So the instantaneous velocity, remember, is the limit as h tends to 0 of that slope of your secant line or your average velocity. So we have that situation of your v instant is equal to the limit as h tends to 0 of fc plus h minus fc divided by h. So we're going to actually have c because we want it at 1 second. So our c is equal to 1. So we're actually looking at the limit as h tends to 0 of 1 plus h minus f1 over h. And now we have to actually put in those values. So we have to remind ourselves, what is the function, and go from there. So our function in our case is, your ft is equal to 8t squared. So now we're going to have our function 1 plus h is going to be 8, 1 plus h squared. That doesn't look very clear. There we go. And let's just multiply it out here so we can put it all pretty inside the actual equation. We have 1 plus h, 1 plus h, and that's 8. That's 1 plus 2h plus h squared. I'm just doing normal multiplication here. And that gives us 8 plus 16h plus 8h squared. Then we have the function at 1, and that is just 8, 1 squared, which is 8. So we're going to put it back into our formula here. And that's 8 plus 16h plus 8h squared minus 8 divided by h. So that's the limit as h tends to 0. That 8 and that 8 cancel out. So we have 16h plus 8h squared divided by h. And we can, take h as a common factor. 8h, scratch that out, and we get 16 plus 8h. And I made a big mistake there because I've got my limit. So let's just put it back in there. Limit as h tends to 0 of 16 plus 8h. And that gives us a final answer of the v instantaneous as 16 meters per second. So at 1 second, the instantaneous velocity is 16 meters per second. And that makes sense because we're like, hey, it has to be lower than that 16.8 meters per second. Now, one of the things to note here is obviously taking your limits. Taking your limits actually really does suck. It's a pretty long process, but we can remember some of the stuff we learned about derivatives. And that is, the derivative of a function is your limit as h tends to 0 of that fc plus h minus the fc divided by h situation, provided that limit exists. So we can actually just use our first derivative in place of taking the limit. So let's go and do some examples with that. Okay, so now we're going to do an example where instead of taking the limit to find the instantaneous rate of change, we are going to use the derivative instead. So we're going to find the instantaneous rate of change for the function f of x equal to x squared plus 3x at x equal to 1 using the first derivative. So the first thing we're going to do is we're actually just going to take the derivative. So we have a function. Our function is f of x is equal to x squared plus 3x. And we're going to take its first derivative. So that is 2x plus 3. And at this moment in time, I'm going to remind you that you're going to have to know your derivation rules to do the work from this point forward. And if you're not comfortable with them, you need to go practice them some more. Okay. And now we want to find the instantaneous rate of change at x equal to 1. So we just substitute in x equal to 1. So we have f prime 1 is equal to 2, 1 plus 3. And that's going to give us 5. So we now have, the instantaneous rate of change at x equal to 1. If we did the long way, or the original way that we were discussing earlier, where we take the limit as h tends to 0 of the function at c plus h minus f of c divided by h, we would have to first find, our function at c plus h, which is, x plus h squared plus 3x plus h, and c, where c is equal to 1. So we actually have f1 plus h is equal to 1 plus h squared plus 3, 1 plus h. We would also have to find, our function at 1, which is your 1 squared plus your 3 multiplied by 1. And then we have to put it into this and still then take the limit as h tends to 0. So as you can see, obviously, using your derivative is going to give you a lot quicker of an answer. But there are some other things that we can, look at when we look at instantaneous rate of change that tells us information about the function without actually having to plot the function. So another thing, instead of just learning what the instantaneous rate of change is at a specific point, we can be like, well, where in our function is there no change? And that's going to help us because where there's no change, that's usually a turning point kind of a situation. So it's an inflection point, the whole turning point that you're comfortable with or familiar with, with your quadratics and stuff like that. So let's go ahead and actually find that. So let's determine where the function is not changing. So where the function is not changing, let's just look at, something like that. It's basically where the rate of change is equal to 0. In other words, when it's parallel to the x-axis. So it's like that kind of situation over there and that situation over there. If you had that sort of function, the function we have is actually just, normal parabola situation. So it will be something like that. But the idea is you will look for where the first derivative is equal to 0. So let's do the first derivative again. And let's keep consistent with coloring. Our first derivative is equal to 2x plus 3. And we just go, okay, where is this derivative equal to 0? Where is it equal to 0? We then say 2x plus 3 equal to 0. So that gives us 2x is equal to minus 3. And x is equal to minus 3 divided by 2. And that is where the function is not changing. So this point over here has the x coordinate of minus 3 upon 2. We don't really care about the y coordinate. Right, we can find it, but we don't care about it in this situation. So we have, that where's the function not changing. That's obviously, again, useful because it tells us turning points. Then we have the situation of if we want to know an idea about the function without, again, plotting the function, we can use this where is the function not changing and then also investigate whether the function is increasing after that point or decreasing after that point to give us, again, that general shape of the function, an idea of where it's going and what's happening with it. So we can also ask the question of, hey, where is it increasing and where is it decreasing? And if we do that, once again, we need actually that point where is it actually not changing? And then we investigate a little to the left of that point and a little to the right of that point. And the reason why I'm using the words a little to the left and a little to the right is because sometimes you have more than one turning point. Again, thinking about, something like that. And you don't want to take a point chilling over here because it's not going to accurately represent this entire area. So you take just a little bit to the side of that point to give you an idea of what's happening around that region of that point so that you don't mess up when it comes to when you actually have more than one point where it's not changing. But it's a little bit to it, but it's up until wherever the next change is kind of a situation, or if there is an inflection situation occurring. Right. So our one that we're investigating is just, let's not draw that line. It's just that kind of situation. So we're only going to have 2 points. We're going to have one side is increasing and one side is decreasing. And when we're talking about, we look a little bit to the left and a little bit to the right, it's going to give us a gradient at a point here and a gradient at a point there to tell us, increasing, decreasing. And when you read it, you usually read it in that direction like that. But what's useful is we know that first derivative gives us the slope. So we know that now when that slope is positive, the function is increasing, and where the slope is negative, that function is decreasing. So let's actually just go ahead and do that. So we have our first derivative. It's 2x plus 3. We know that the first derivative is equal to 0 at x is equal to minus 2 upon 3. So again, we're going to look a little bit to the left, a little bit to the right to investigate what happens to our first derivative. So I try to be as lazy as possible when I choose my values because, well, who doesn't want to be? And so when I'm looking at to the right, I'm going to choose 0 because anything multiplied by 0 really makes your life easy. So we say the first derivative at 0 is equal to 2 times 0 plus 3, which is equal to 3, which is greater than 0, which means increasing. Okay? And then, so now we have where x is greater than minus 2 upon 3, f prime x is greater than 0, and therefore the function is increasing. Right, so technically at this point we should know, because that rate of where the rate of change is equal to 0, it's usually where it's changing direction. We should have, then anything less than minus 2 upon 3 is decreasing, but let's actually just go do the math anyway. So I'm going to choose minus 1 to make my life a little bit easier kind of situation. So we have minus 2 upon 3. More negative is that minus 1 or minus 2, minus 3 kind of situation. Ooh. I did this the wrong way around. It's minus 3 upon 2. Wow. Yeah, I had it correct on the other page. So just be very careful about that. X is minus 3 upon 2. So we are going to have to choose minus 2 as an example. We can't choose minus 1 because minus 1 is obviously sitting in that range over there with that minus 3 upon 2. So a reminder, I made a mistake there. I swapped my 2 and my 3 around. Our turning point is at minus 3 upon 2, so we have to choose a value to the right. We chose 0, that one was cool. But we also have to choose value to the left. Obviously, I can't choose minus 1 because minus 1 is bigger than minus 3 upon 2. So let's choose minus 2. So we say f prime minus 2. 2 times minus 2 plus 3. That's going to give us minus 4 plus 3. And that's going to give us minus 1. And that means that it is less than 0, which is decreasing. So now we have where x is less than minus 3 upon 2. Our derivative is less than 0. Therefore, the function is decreasing for anything less than minus 3 upon 2. Right, so we've worked out that we can use the first derivative to actually just find the instantaneous rate of change at a point. We worked out we can find out where our function is changing directions by setting our derivative equal to 0. And we've also worked out we can determine if it's increasing or decreasing, utilizing, if it's positive or negative. So one of the other things that we need to consider is slightly more difficult examples. So we're going to use the cos example here, because when we do this working out, it's not necessarily going to be as simple and pretty as that easy example that we did. So we're going to use cos so that you can remind yourself that sometimes there will be multiple solutions which will fit the answer. So in this case, we have f of x is equal to 5 minus 6x minus 10 cos x. And we're going to determine where is it not changing. So we're just going to look for where is that derivative equal to 0. So if we go through this process, let's just write down the function first. 5 minus 6x minus 10 cos x. Our first derivative is minus 6 plus 10 sine x. So remember, cos of x, the derivative of cos of x is minus sine x. So the minus and the minus become that positive in front there. Right, so we have our first derivative. Great. Now we're like, okay, where is it equal to 0? And at this point, you're like, oh, this work is easy. So let's go through there. Minus 6, 10 sine x is equal to 0. We have the 10 sine x. We have the 6 over there. sine x, 6 over 10. X is equal to sine minus 1, 6 over 10. Don't forget we work in radians. So your calculator needs to be set into radians in order to get this answer. And we get 0.6435, etc. We're just going to work with the 4 decimal places here. So at this moment in time, you may be like, okay, I'm done. You have to remember that when you have cos, sine, and tan, things repeat, and there's certain things you need to consider in this. So yes, where x is equal to 0.6435, your first derivative will equal to 0. But, and let's just draw this so you can remind yourself about this. Whenever you have your sine graph, remember there's one iteration of it, then you have another, then you have another. So technically, every 2 pi, you will have a value that fits this condition. So you need to take that into account. So to deal with the repetition, we have to say, okay, where x is equal to 0.6435 plus 2 pi times n, where n is just the element of, your integers. And then you're like, okay, great. So we have, n is equal to, your 0, your 1, your 2, your 3, your 4. However many iterations you have is going to fit. Also your minus 1, your minus 2, your minus 3, your minus 4, and so on. But, and this is another thing that you need to remember, again, it's very specific, to this kind of cos, sine, and tan situation. And that is, you need to consider your unit circle. So a reminder about your unit circle, you had your angle, chilling over there. You would have a representation here of pi minus the angle, representation here of pi plus the angle, and a representation of 2 pi minus the angle. So you have your cost diagram that you need to consider. So your cost, and that tells you which ones are positive in, which area. Again, it's to do with the whole repetition situation that sine, cos, and tan have. So now we're like, okay, technically, when we look at this, and if we have sine theta, it is also, or it can also be represented by sine pi minus theta. So we need to consider that. So your sine pi minus theta is equal to your sine theta, or in our case, sine pi minus x is equal to sine x. So wherever, you have your x, you need to consider the situation of pi minus x as well as a value in which it would meet those conditions. So be very careful, particularly with your whole trig situation. You have your repeating aspect. It repeats every 2 pi. We covered that part, but we also have our unit circle where, the things are the same kind of a situation, which is also going to work out. So we have a second batch of x's to consider, and that is x is equal to pi minus 0.6435 plus 2 pi n, which is equal to 24981 plus 2 pi n, where n is an element of integers. Okay, so it does get more complicated than just taking the first derivative. You need to consider other factors of information that you have learned in the past to finalize your solutions. But in this case, you have to consider your sine, your cos, and your tan are repeating periodic functions. And then you have to consider your unit circle. So another example of just like your unit circle kind of situation, if you had cos theta, for an example, you would then look at your cos 2 pi minus theta situation. So just keep that in mind when you're doing additional examples, particularly when it's related to trig. There will be additional solutions where your function is equal to 0.